Louis Thompson is a senior engineering scientist, partially retired, at Applied Research Labs at the University of Texas at Austin. He's a registered professional engineer in the state of Texas. During his 44 years of employment, he worked the areas of underwater acoustics and radio communications. He's been a licensed amateur radio operator since 1961 and is now licensed extra class. He has held amateur radio positions, including president of the Austin Amateur Radio Club, RACY's district radio operator, DRO 62, and assistant emergency coordinator for TCARES. He's currently the vice president of the Austin Amateur Radio Club. He joined Texas Army Mars, the other Mars, not us, in 2006, and served as state Mars director from 2009 to 2011. And so I'm going to also say thank you for your service. He is the liaison to the Texas Military Forces for Texas Army Mars.
Good evening to everyone. This presentation had a specific audience, which was dismounted Texas National Guard, let me turn off my cell phone here, which was Texas Army National Guard commo teams. Dismounted means they don't have amplifiers, they're not in Humvees, they're on foot. So they have basically a 20-watt radio, and we'll talk more about that. I was constrained in the subject matter that I could talk about by Army Netcom Fort Huachuca, because they want specific information. I've expanded it some for the Army Mars program and for amateur radio consumption. Next slide. So the objectives are to teach the soldiers how to utilize equipment and supplies that can be found locally to construct field expedient antennas when the purpose-built HF antenna is not available. It turns out the only antenna they have available is a very poor wideband antenna that typically at NVIS frequencies lowers their output, the effective radiated power, down to about 0.5 watts. And so for some strange reason, they all felt like that HF radio just didn't work. So I've tried to change that capability by improving their antennas. And the second objective was to build an emergency antenna for use when existing HF antennas are not available, so that they could carry something with them that they could build a little bit before they actually had to deploy. Next slide. So there's a specific amount of radio hardware that needs to be available. The typical PRC 150 radio has a very good built-in auto tuner that allows it to operate over a wide range of frequencies, both for frequency hopping, which is used to hide their transmissions, and also allowing them to move up and down in frequencies to address different circuits. And so that's an important capability that their PRC 150 has, a very good auto tuner. If they do not have an auto tuner available, then they are pretty much limited to building a single frequency resonant dipole. I'm going to talk about one other radio which has ability with a pretty good auto tuner also. All of the HF rigs that we own, from ICOMs to Kenwoods, etc., do have a built-in auto tuner, but that auto tuner is limited to working with standing wave ratios of 3 to 1 or less. That is because if you had a wide-ranging auto tuner, the voltages inside the radio could certainly get to be kilovolts if the impedance you're trying to match to is kiloohms. And that's why the external auto tuners you see have glass insulators on the output end. So we're very limited in what our radios can typically do to match antennas. Next slide. Okay, the Army's standard radio, which is about to be replaced, is the ANPRC 150. It has encryption, digital voice, etc. And but its maximum output is 20 watts. Because that's about as heavy a battery as a foot soldier can carry to operate this radio. It has an outstanding auto tuner, and I did a lot of testing on this radio before it became apparent the problem with antenna, with their lack of transmission capability, was their available antennas rather than the radio itself. So an outstanding auto tuner can match just about anything you connect to it. Next slide. Much to my surprise, I found one other radio in the inventory that has a very good built-in auto tuner that has wide-ranging capability. And this is the Chinese Xiegu G90. It's also a 20-watt radio, and it can just about match any piece of wire you can put up, just like the PRC 150. So other than these two radios, I'm not aware of any radios with built-in tuners that have this range of tuning. So these two radios allow the use of wideband antennas whose impedance is vastly different from 50 ohms, or at least a 3-to-1 SWR impedance. Next slide. So I think everybody knows this. Again, remember that this presentation is directed to Army commo teams that have forgotten what they learned in their radio classes years before. So there's two types of basic antennas: the dipole, which we call also the Hertz antenna, and the vertical or Marconi antenna. The vertical antenna is not good for near vertical incident skywave propagation, which is what I was really teaching in this class. Next slide. So I think a little bit of history. The dipole antenna was developed by Hendrik Hertz around 1886 in his pioneering investigation of radio waves, and the dipole is considered a balanced antenna. Next slide. Of course, it's not required that a dipole antenna be horizontal, but in most cases, it's impractical to try to build a vertical dipole. I do have a vertical dipole antenna that performs well, but it starts at 14 megahertz. That's the gap type antenna, works well, but we're not going to even discuss that type of antenna today. For the following discussions, I'm going to assume all of the dipole antennas are horizontal. Next slide. So again, this is straight out of the Army textbook. A lot of the transportable equipment will often use relatively short paths for which the half-wave dipole is well suited. This can be set up for the NVIS operation, or if you put the antenna up high enough, it can do a much better job. A table that is in their manual is on the next slide, please. This antenna basically shows the horizontal path distance in kilometers versus the antenna height in wavelengths. So one curve is the optimum curve, the upper curve, and the bottom curve has a 3 dB penalty because you can't get your antenna up high. If you'll notice, at distances out to about let's say 400 to 500 kilometers, you're in the NVIS region, and sure enough, the antenna height is about 0.2 to 0.25 wavelengths above the ground. And so that fits perfectly with our understanding of how you build an NVIS antenna. And that's what most of these soldiers were trying to develop. And it does work to some extent if you are much lower, but you lose half your power at least. And notice when you get out to about half a wavelength, the distances are about 1,200 kilometers. So this helps the soldier determine height versus antenna height versus the kind of range he wishes to achieve. But more important than this is the fact that the directivity pattern of the antenna changes with height. Next slide. So this is kind of a busy slide, but what we have is 4 different elevation plots, either in-fired, along the wire, or orthogonal or broadside to the dipole. And the first antenna at the top shows the elevation pattern for along the wire and then broadside to it. And as you can see, both of these patterns produce a NVIS cloud warmer type signal, which means most of the energy goes straight up and bounces off and gives you the short NVIS ranges you want. Notice that it is still asymmetric, but it's still useful. When you go to a half wavelength, the next pattern, you'll see that suddenly the broadside pattern becomes shaped like a donut in 3 dimensions. All the energy goes out at a relatively low grazing angle. And I'm sorry, that is incorrect. That's a vertical antenna. This has a cosine pattern that comes off the broadside of the dipole antenna, and the end-fire signal is very low. So this would be a good antenna for long range as long as you pointed the broadside pattern, the broadside of the antenna towards your recipient. As you go up higher, 3/4 of a wavelength, the vertical pattern starts to break up and then you lose a lot of energy going straight up instead of going out at low angles, which you wish. So getting up too high is a bad thing. And even at 1 wavelength high, the antenna is still putting a lot of energy at 2 different angles. Might be useful if you want to have both mid-range and long-range capability, but again, it's scattering your energy over different angles. Next slide. So to emphasize this pattern, here is a dipole at a half wavelength height. And broadside to the wire, it has a cosine pattern with the energy, at about 25 to 30 degree takeoff angle. So this would be a good antenna for 1,000, 1,500 mile ranges. Next slide. In contrast, you take that same dipole and put it down at a 1/4 wavelength above the ground. And as long as you're operating below the local critical frequency, this signal would go up, bounce off the F2 layer, and come back down and have good reception out to about 400 or 500 miles. And this is basically what amateur organizations like Aries and RACES want to do to get statewide coverage, and the Mars program, in order to operate over Region 6 in the central United States, use these same type of antennas. Next slide. So I think everybody knows what a half-wave resonant dipole is. Sometimes our soldiers don't, so I have this interesting picture. The antenna is a half wavelength. Each half of the antenna is, of course, a 1/4 wavelength, and it's driven by coaxial cable, because the antenna, when it's exactly operating at a half wavelength frequency, will have a terminal impedance pretty close to 50 ohms, so that you can drive this with coaxial cable without any losses. Of course, you can turn this into an inverted V and use only 1 vertical mast. Next slide. So half-wave resonant dipoles, again, this is if you don't have a tuner with the radio. It operates on only 1 frequency and a very narrow bandwidth. The total length is 468 divided by the frequency in megahertz, and I'll have a table on the next slide. It's relatively simple to build, but requires careful tuning. You can use coaxial cable, and again requires no tuner. Typically, you want to use a 1-to-1 balun to balance the load because the coax is single-ended with one end to ground, and you want to have both sides of the antenna being driven symmetrically, so you need a 1-to-1 balun. Next slide. So this is a convenient military table that gives you bands of frequencies, and then on the right side is the half wavelength in the same band of frequencies, so that a soldier or an amateur can get relatively close to the half wavelength dimension he wants for his antenna. He will then use the procedure on the next slide to tune it to the exact frequency. So the first thing you do is pick the best guess you can, and you install the antenna using table 1 in its final configuration, whether it's inverted V or a dipole, and you simply vary the frequency slightly using either your radio or your an antenna analyzer until you find the lowest SWR frequency, and that's F sub M. Then you're going to adjust the length to move the resonance to the required frequency, and you do that as follows. The required length is simply equal to the lowest SWR frequency divided by the F sub R, the resonant frequency you wish, and times the length that you cut the antenna to. And so I'll give you an example. You basically want to build an antenna, let's say, that resonates at 5.202 megahertz. You initially cut the antenna to 95 feet. You measured the resonance and it was wrong. It was 5.4 megahertz. This will probably result in an SWR greater than 3-to-1. Therefore, you need to increase the length by 5.4 divided by 5.202 times the original cut length of 95 feet. You come out with a result that the antenna really should be 98.6 feet. In other words, you need to increase the length of each half of the dipole by half that difference, or 1.8 feet. And the antenna, I'll guarantee you, will resonate at exactly 5.202 megahertz without any cutting and testing. Next slide. So now we know how to build a resonant dipole, because we don't have anything but a simple radio, or our radio has a very low capability auto tuner. So now we're going to talk about building non-resonant antennas, because we do have a high performance auto tuner of some type. We're going to talk about 2 different kinds of antennas. One is a balanced wideband dipole, which is a very good performing antenna, and the other is a long wire. Again, it is assumed that the user has a wide range auto tuner available to couple to wide bandwidth field expedient antennas. Coaxial transmission line links, if you happen to want to use them, need to be minimized to reduce the dielectric losses in the coaxial cable. Typically, a Mars operator will run ladder line down to a balun, and then coaxial cable into his shack where his auto tuner is, so that it doesn't get damaged by lightning or by weather. But it's very important that you realize that when you have high standing wave ratios on coaxial cables, that they have dramatically higher dielectric losses than you would measure when the antenna was matched to 50 ohms. What is really recommended is to use open wire transmission line, which has air in between the wires and has effectively no dielectric loss. And again, I'll emphasize this another time. The wideband dipole with ladder line needs about a 4-to-1 balun if you're going to run transmit a coaxial cable after that. And for a single-ended long wire, it's nice to have about a 9-to-1 balance. Next slide. So here's the non-resonant dipole. Some people call these doublets. Basically, an example of an NBIS non-resonant dipole is inverted V with leg lengths of 65 to 75 feet, a height 30 to 50 feet. You want to get the angle as high as you can, so that you want to have about a 10 or 15, 20-foot guy ropes at the ends to get the driven ends of the antenna up a little bit. Note that the ladder line then attaches to an automatic tuner, antenna tuner. Notice in the upper right-hand corner, for those wanting to build this type of antenna, that there's a very nice device called a ladder lock that's sold almost by any amateur radio supply house that allows a way to attach 400 ohm transmission line to 450 ohm transmission line to the antenna wires, and in such a way that there's little or no fatigue and strain on the ladder line. I highly recommend this device. I've had some up that have been up at Camp Mabry for 10 years. Next slide. So the other option you have is the long wire antennas. Long wire are simple. It's easy to construct and can be used to improve the transmitting and receiving of the radio. The PRC 150 basically comes with a whip antenna that won't even talk across a parking lot most of the cases. Very poor antenna of no use. And the long wire improves efficiency by getting a horizontal wire up that's bigger and at a greater distance above the ground than for a vehicle or a man-portable whip. Next slide. The long wire that I analyzed and recommended to the dismounted infantry commo teams is a long wire. It has both good performance below 10 megahertz for NBIS, and that at frequencies greater than 10 megahertz, it becomes directional and performs reasonably well. As I show in the diagram, I suggest a 100-foot piece of wire. It's 30 feet at one end. You throw a rope over a tree and pull up the wire, and the other end connects to the transceiver auto tuner, and the auto tuner's counterpoise is connected to the ground. Or you can run a counterpoise wire on the ground underneath the 100-foot wire. Notice that the direction, the lowest angle of takeoff is in the sloped direction along the wire with the desired station towards the transceiver. Next slide. So here is an example modeled by me with using EasyNet for 5.2 megahertz with a 100-foot wire. As you can see, it has a good NVIS pattern. Its gain is reasonable, works quite well. Next slide. The same wire, when you operate at 18 megahertz, has an interesting pattern as seen in the lower left-hand corner. And then the upper right-hand corner shows you the two lobes. The lower lobe is the one that's towards the receiver, the transceiver, as I showed in the diagram 2 slides back. And so this could be a reasonable antenna. And again, its gain, 2.76 dBi, is not unreasonable. So this gives you a capability. And the National Guard commo teams built these, put them up, and they were actually able to talk around Texas reasonably effectively, like from Austin or Round Rock to Waco to Houston using NVIS mode. We didn't really have any stations that were farther away that they could try, and probably with their power levels, they wouldn't have had much luck. Next slide. So the supplies that you need to either build a long wire antenna or a wide or dipole antenna is you need antenna wire, which can be 14 to 18 gauge stranded, preferably insulated, 75 to 150 feet long. You need to have something where you can make insulators, either for the dipole or for the long wire. And you can certainly use dry rope. Water bottles, we actually had them cut holes in a water bottle and run the wire and the rope, guy rope through it, and that works just fine. It would be nice to have some clamps and pulleys in your box so that you can hoist up the antenna. You'd need some synthetic rope, parachute line, etc. Counterweights that you could put on the end of the rope to provide a throwing capability, etc., and some carabiners. Supports can be flagpoles, push-up poles, structures, trees, etc. And then here, for no other reason but needing to have it here, I put in some ballons made by the company called Ballon Designs, and 3 different model numbers. One is a 1-to-1, one's 4-to-1, and one's 9-to-1. These are all 100-watt ballons. Very good company and a very good product for sort of carrying with you in your ready box. Next slide. So this is just an example of the throw rope that was in the combo manual for the National Guard, and something to be made up and put away. Next slide. So long wire setup options. Pretty much any way you can string the wire, but the upper 2 pictures, which I've never tried, have, you might say, a limitation, because not only does the horizontal wire radiate, but when you model this antenna, you must also take into account the vertical wire going up to attach to the horizontal wire in both upper cases. And this can certainly modify the directivity pattern, and in a lot of cases, reduce its effective gain. So these are certainly last resort plans of action. The sloped antenna shown in the lower right hand is the only antenna that I felt like deserved sufficient work to teach the soldiers to build. Next slide. Long wire antennas have significant disadvantages. It, of course, requires that the transceiver or antenna tuner to be located at the end of the long wire. Very difficult to put transmission lines on these kinds of antennas. Any radio with a built-in tuner is exposed to the weather. If you use an external auto tuner, it must be weatherproof. And the big factor in this case for the military teams using the PRC 150 is that this exposes the soldier to enemy fire. Putting the radio on top of a hill with a long wire antenna is exactly what soldiers don't want to do, because as I think everyone knows, the first thing snipers shoot at are officers. The second thing are radio operators. So they want to be down in the ground. They want to have transmission lines that lead from the antenna down to the foxhole so they can be out of the line of fire and maybe a little bit away from that mountaintop location. So long wires have real disadvantages, and I have emphasized trying to use antennas that work well with transmission lines. Next slide. So what I suggested, and this was not Netcom's suggestion, I decided I would put together 2 different possible kit designs that the soldiers could build in their spare time and start to pack up and take them with them, so that they'll have an adjustable antenna that is useful and can be quickly put up but didn't cost much money. And so the first antenna is the single frequency adjustable dipole, and the second will be a wideband dipole with ladder line. Next slide. So this antenna is modeled after the old Army GRA 50. Some of y'all that were in the military a long time ago, you may have seen something similar to this. It's basically, in this case, 2 fly fishing reels with 85 feet of flex copper wire on them, with a way to secure the wire at different lengths, and then a one-to-one balun. And this is adjusted to a resonant frequency. I can supply complete design instructions for this. And in fact, several members in the Mars program and one in the Austin Amateur Radio Club have actually built this antenna. This antenna actually went to Somalia with an infantry team and survived the Army, an infantry unit, and came back in one piece. Next slide. So basically, you can deploy this antenna either as an inverted V with each leg at 223 divided by the frequency in megahertz, and there's 100 feet of RG8X coax. But remember, if the antenna was resonant, the coaxial cable loss is minimal. So this is one way to deploy it for NVIS. Next slide. The other way for long-range communications, you would like to have the antenna horizontal, but you can sort of approximate that by simply stringing it out from the post. And of course, the length of the wire is going to be considerably less. And so with a long piece of rope on the end, you sort of end up with a almost horizontal dipole that will give you good cosine type long-range broadside communications. Again, you have to point the broadside of the antenna towards your recipient. Next slide. So in this kit, I included a 100-foot tape measure, a carrying case, 100 feet of coaxial cable, RG8X, and then a table of frequencies versus dimensions so that they can get close to the correct dimension. Next slide. Frequency adjustment with the two 85-foot pieces of wire. It can be resonated from 2.75 megahertz to 30 megahertz. I actually tested this. One-to-one balun. It's a number 14 American wire gauge flex weave. Breaking strength is 110 pounds. The working load's 30 to 60 pounds. Keeps everything safe. Measured SWR was no greater than 1.2 to 1 at the end of the 100-foot of coaxial cable when it was at resonance, and coaxial cable losses at that low SWR is about 0.8 dB per 100 feet at 10 megahertz. Next slide. So this is just a list of all the components, and the total weight was 11 pounds. And I can provide details. The greatest cost. Well, next slide. Let me see if I have costs on it. Okay, back. So for this antenna, I can provide complete building instructions and cost. The biggest cost items were the Prestige fly rod reels from Cabela's and the 200 feet of copper flex weave. Everything else is relatively inexpensive. The second antenna, which is much more useful to the military and to amateurs, is the wideband dipole, as shown here with a 4-to-1 balun. Next slide. So it is typically suggested that it be put up as a inverted V. You can certainly change the length of the legs of the antenna if you wish to go up in higher frequencies. I simply set it up for NVIS propagation, which is how it was used. Next slide. In this case, the Easy Neck model, 67 feet on each leg. The apex height was 32 feet. The end heights was 7.7 feet. American wire gauge number 14, stranded insulated copper. The transmission line is 300 ohm transmission twin lead. The ladder line length for this transmission line was 40 feet, but I have tested it at 60 feet, and the balun was a 4-to-1. This antenna worked very well with the PRC 150 and the Xiegu G90 at all NVIS frequencies. Next slide. So here's just the parts list. All comes from DX Engineering. Relatively inexpensive hardware to allow you to tie wrap and strap the 300 ohm ladder line down. Here is the 300 ohm transmission ladder line. It's not your basic TV ladder line. It's designed for transmission. It's relatively tough and certainly survives the military. And I'll tell you exactly how it's been tested. Next slide. Here is the premium antenna wire from DX Engineering, number 14, stranded copper insulated, and then enough synthetic textile rope for providing the ends and the hoist in the middle. Next slide. So I even included a toolbox and a reel, and then the balun is a 4-to-1 from a QRP 4-to-1 balun from Balun Designs. Total cost for this antenna kit was $187.05, probably a little bit more expensive now because of inflation. Next slide. So the specifications for this antenna: frequency range 2 to 30 megahertz, and really depends upon the performance of the tuner. Balun was 4-to-1. Wires number 14, American wire gauge copper insulated. The 300 ohm ladder line has 0.48 dB per 100-foot loss at 10 megahertz. Notice that that's less than the RG8X. And I have finished testing this same antenna with 60 feet of 300 ohm ladder line. A little bit about auto tuners. External auto tuners are made by SGC, MFJ, and LDG. There may be some others, but that's the ones I have familiarity with. Only the SGC and the LDG external tuner are waterproof. The MFJ tuners, which appear to be waterproof, are not, and really need to be significantly upgraded if you wish to have their case to be watertight, or you need to mount them in a box to keep them watertight. But when they are not wet, they perform very well and have very wide frequency tuning ranges. A word of caution: I have found that the LDG tuners do not have as wide a tuning range as SGC or MFJs. They simply have smaller values of inductors and capacitors inside them, and do not tune over as wide a frequency range as the or impedance range, you might say, than the SGC and MFJ. SGC is certainly the gold standard in their SG230 tuner. It's the finest tuner on the market that I'm aware of. Typically, a military mounted unit will have a dipole antenna with 300 ohm ladder line going straight down to the ground, where there is a watertight, waterproof auto tuner. And from there are the control cables and coaxial cables that run into the Humvee, where the radio and amplifier are located. And this works very effectively. And so we're hoping someday that Harris or someone else will produce a very small military auto tuner that soldiers can use in a similar fashion with the PRC 150 or the new PRC 160 barefoot. But presently, that doesn't exist. Next slide. So, conclusions. A field expedient antenna will allow the Mars amateur operator to communicate when its existing antenna is not available. The frequency agility of the field expedient antenna is greatly enhanced with a wide range auto tuner. The dimensions, length, and height control the antenna performance. Very important. The height and the wavelength dimensions will control exactly the directivity pattern and where the signal is going to go. You have to take this into account. The two jump kit emergency antennas that I've shown have been extensively tested by the Army National Guard teams at Fort Polk, Camp Mabry, and Fort Hood. In fact, the adjustable antenna went to Somalia for 6 months with a dismounted infantry, National Guard infantry combo team. So it does, both of these antennas do work very well. My favorite is, of course, the wideband antenna because it can be used for narrowband frequency hopping, and the auto tuner in the PRC 150 can actually follow and retune the antenna during the frequency hopping situation. But wideband doesn't work, and there's no reason to even try that because the auto tuners don't work. And of course, wideband frequency hopping with a ionospheric skip circuit has no meaning because you'll just simply skip out of the circuit range. So narrowband NVIS frequency hopping was tested at Fort Polk and worked very effectively. Next slide. Any questions? Once again, this was a simplified presentation designed to teach Army National Guard members the rudimentaries of developing expedient antennas so that they could make HF work. Questions?
Okay, we're going to take questions from the room, and then I'm going to kind of help out the folks on Zoom. So we've got a question from the room. Here we go.
I was just curious if there's any significant difference among the antennas you talked about in terms of the noise level of the antennas.
I really haven't noticed. Certainly, we're down at NVIS frequencies, which are very noisy. Certainly, horizontal antennas have less noise because most ambient noise is vertically polarized. So any form of horizontal antenna will be quieter. It would be interesting to compare the noise between a long wire and a balanced dipole. And I really, again, the PRC 150 has really no way to measure noise. It does not have an S meter. So it's very difficult to do that. So I would say as long as we stuck with horizontal antennas and didn't go to a vertical antenna, noise would probably not be much different.
I have a question.
Yes.
Okay.
On the reels, the fishing reels, how do they impact the tuning? Let's say if you set it for 20 meters and you still got quite a bit of wire on those reels.
Well, say the wire is uninsulated copper, and so as you reel it on the reel, it just becomes a knot of copper.
Okay.
And I realized that probably modifies it because it's all connected together to the aluminum holder. So I carefully built my dimension table by actually resonating the antenna and then writing down the length that caused it to resonate at X megahertz. And it didn't seem to be much different from the calculated inverted V dimensions that I calculated. So it didn't seem to make a lot of difference, but it's just a block of copper out there at the end because it's all connected together.
Okay, thank you.
Yeah, I did try building an insulated version of this antenna on a bigger reel, and it didn't work good at all for exactly that reason. Because if you have an insulated reel at the end, it's an inductor, and it modified the resonances of the antennas pretty badly. So what was important was that all of that wire that's wound together all is conducted together.
Makes sense. Thank you.
Other questions? Again, this was a simplified presentation for Army members. I certainly have much more complex antenna designs that I have worked with the Army Mars program and mounted Texas military forces.
Lewis, off mic, you didn't know that we actually had a failed battery on the handheld mic, and we had to do a little field swap in between. That's why we couldn't get any. One little bit of feedback here. Bob, the owner and president of Ballon Designs, is a buddy of mine. He actually is based in Denton. So he's not very far from us, and many of us already have. I'm a big Ballon Designs fan. I've got Ballon Designs at home, so it's great.
It's just a great company. They really do an excellent job of properly designing balance. I have a whole book on balance, and there's a lot of things you can do wrong. And,
Bob's amazing.
Bob has done a great job.
Yeah, I've worked with Bob for over 20 years, and he's a. If you go in his, when I went and picked up my Ballon, he's also really big into RC. He's got some really cool RC helicopters, really cool ones. Anyway, any more questions from the room? Okay. One of the things, Lewis, one of the things we'd like to do is a Texas State Parks on the Air, which is a little contest that goes on around the state in the spring. And we've definitely learned our lesson that we need to put up a nice NVIS antenna because, from North Texas to Central Texas is definitely NVIS, not a vertical. So
yes.
Take some of your designs to heart. Anybody on Zoom that'd like to answer a question?
Yeah, how about an additional discussion of vertical antennas?
Well, again, a vertical antenna has a directivity pattern that looks like a donut. Even if you take a 20-foot vertical and operate it at 4 megahertz, it still has a donut pattern, which means no energy goes straight up, and so it does not excite an NVIS type circuit. Vertical antennas do great. I'm presently using a Gap Titan DX, which is a vertically polarized dipole. Its performance is better than that of Cushcraft trap dipole and a 24-foot dipole vertical with 4 ground radials. We actually put these 3 antennas up at Field Day in Austin this year, and I was able to compare the performance of those 3 verticals using reverse propagation Saturday morning before we actually got on the air for our contest. I was the CW captain for that group, and so that worked very well. I am presently doing a propagation study for a customer that is paying me to evaluate some propagation software. And I use a program called Pharos that automatically controls my transceiver and receives all the beacons, the NCDXF beacon system, and that goes from 20 meters up to 10 meters, including the WARC bands. And I repeatedly was able to receive ZL6 Bravo, I believe is the call sign, New Zealand, quite easily when the propagation program said it should be there. And if anybody knows, you may know about the beacons. They transmit their call sign, 22 words a minute CW, and then they transmit 4 DAWs, 1 second DAWs, and it's at 100 watts, 10 watts, 1 watt, and 0.1 watt. And in some cases, I'm able to hear 1 watt from New Zealand using the vertical antenna. The beacons actually transmit to a trap vertical antenna using 100 watts. And so again, when the president was talking about the wonder of HF, that's a good example. New Zealand to Austin, my backyard, I was hearing 1 watt. And imagine the spreading loss. So so verticals can do a good job. Just realize that they have a directivity pattern that is absolutely not NVIS. I get into arguments with brand new Army Mars members that want to put a vertical up because it's very space efficient, but it will not excite the NVIS pattern and get you into statewide communications. Anything else, Steph?
Can you give me the name of your vertical dipole?
Yes, it's GAP, Golf Alpha Papa, Titan, Tango India, Tango Alpha November, and then Delta X-ray.
Did it have a ground
Thank
radius like the?
Oh, no, it is actually insulated in the center, and it's driven as a vertical dipole. It's 30 feet tall, and it has about a 4-foot skirt near the ground that helps resonate the 40-meter portion. This antenna works from 75 meters to 10 meters and is the best performing vertical I have been around. And like I said, I carefully tested it against 2 other dipole verticals that we've been using for years in our field day operations. The vertical with ground radials actually has an AH4 auto tuner at its base, and so it resonates itself. The other
Did you have to pick a specific?
is an R8. Kush crap.
Are you feeding it with coax?
Yes, the Titan, the Gap Titan DX has a bunch of aluminum arms on it that act as tuning elements, and the antenna carefully resonates at each of the amateur bands from 80 meters on up and wavelength, and on down, I guess in wavelength, 75 meters to 10 meters. And it's driven by coaxial cable, and the SWRs are less than 1.5 to 1. It's really an amazing American-made product. I have been very impressed with it, and I do antenna modeling and design, and I couldn't begin to model this antenna. It's very, very complex. Takes probably a day to construct it. It's all aluminum, and stainless steel screws, but it performs very well.
Thank
Highly
you.
recommend it. Yes, sir.
Yes. Have you evaluated end-fed half waves for NVIS?
Not really. I should, but I have not. Again, the long wire antenna that I showed is the only real long wire that I evaluated, and it had a good NVIS pattern at 5 megahertz, if you'll remember from my plot. That's the only one I've ever tried.
Did you have to pick a specific frequency, a narrow frequency band on that Titan antenna for 75 meters?
Yes. You when you buy the antenna, they ask you if you want the CW portion or the phone portion, and they send you one of 2 different values of capacitors that, believe it or not, mounts at the top end of the antenna.
Okay, I had a challenge.
And you clamp, you connect it, and sure enough, that antenna worked in the phone portion of the 75 meter band. I'm going to probably go ahead and buy the other capacitor if I want to get down in the CW portion.
Yeah, I had a Challenger and it had the same arrangement, but they wanted radials. And
yeah, this just has vertical components. In fact, I'm in a covenant restricted neighborhood, and so while I'm allowed to have a few antennas next to trees, this one's out in the middle of my backyard, and it's relatively easy for me to stand it up and lay it back down without having to take anything but the skirt off. I simply drop the 40-meter rectangular skirt to the ground, and I just lay the thing down with the tilt base, and it's out of sight. And there's no radial, no ground, no radials anywhere else on the antenna, unlike my R8 that has 2 different sets of radials part of the way up.
Are you using an auto tuner with the Gap antenna?
No, not at all.
Since it's a resonant antenna, Seth, you don't need an auto tuner because it has resonant frequencies on different bands.
Right.
So just in general, Seth, just as you're a physician, you do realize that you have to pick the right antibiotic for a specific need. So you got the right tool for the job.
Okay.
Verticals are great for long distance DX because of that low angle radiation. So in general, verticals are great for that. NVIS antennas, which we've talked about today, are great for medium to short haul communication. So we've got two different antibiotics to apply to this problem. You've already got one. You've got a vertical. Maybe it needs a little tune-up. That S9 vertical 43 is not a bad little antenna. A little bit of fixing up on the radials and stuff. And then with a simple dipole, you might be able to just sort of add a better dipole to your antenna farm there in Metairie and have a better choice of tools for the job.
Well, Seth had his vertical kind of field tuned by the last hurricane.
Yeah, I kind of suspected that S9 kind of got a little damage there. But just in general, just that gap is a $600 antenna to start. Just to let everybody know, it's a nice skyhook, but it's a little pricey.
But it's the same if you pay for an R8 or R9 push trap, they're all expensive. And they use traps, which are lossy. This has no LC traps anywhere on the antenna. And as I said, we compared AB within a huge field at the American Red Cross building in Austin. And it was the best opportunity I had to test 3 different antennas. And I was impressed. Definitely.
So the one thing I've learned about antennas is they're a lot like pickup trucks. They're very religious. Everybody's got their favorite. You've got your Dodge and your Ford and your Ram fans, and it can get quite contentious in discussion. So just in the sake of time, last call for some questions. Lewis, this has been a fantastic discussion on NVIS and antennas. We really enjoy talking about antennas. Last call for questions. I'm going to ask, is it okay if we post your presentation a little later on our website for folks to?
Absolutely, and realize that I have done a lot more than what this presentation entailed. This was specifically to teach newbie Army communicators. And the first day, they didn't even understand how HF got from Fort Collins, Colorado to Austin, Texas. They had repeaters trucks all the way from Colorado to Austin because it's all that they knew, VHF repeaters. And the end of the second day, they were building antennas and talking across Texas with HF 20-watt radios. So all those people needed was just a little education, and that's what the purpose of this presentation and several others that I did to them was. I can certainly expand.
Showing them the magic of HF.
Absolutely, and we're going to have to be able to do that because we've got enemies that can disable our satellites and our internet. So we're the last resort. We've got to teach the military and everyone else to do HF.
Indeed.
And I'll get off my soapbox now.
And in general, Seth, also when you're listening, feed lines are important.
Yes.
RG8X is fine for some things, but it's really, put your money in your feed line. I know a lot of us feed it with LMR 400 or better.
Yes.
There's lots of choices in feed lines and stuff. That's a whole nother discussion we can have.
Yep.
All right. Well, Lewis, again, thank you. Well, that's a big round of applause. Thank you very much, Lewis. We appreciate you coming in from Austin and remoting in to give us our presentation tonight.